So next on the docket, we just talked about rate expressions. Rate expressions are ways of measuring the rate of a reaction. What is a rate law used for then? It's not a way of measuring the rate of a reaction. What are laws for? If I let go of this marker, where's it going? To the floor, based on what law? Law of gravity. Laws allow us to make predictions about the future. If I know the initial conditions, i.e. if I let go of this marker, what would happen? It would drop to the ground. Same thing here. A rate law allows us to predict the rate of a future reaction. If I know the initial conditions, the initial concentrations of reactants, how fast would that reaction go? That's what a rate law is for. So, and if I had a reaction like A plus B turns into C or something like that, a rate law generally depends on the concentration of the reactants. Not usually the products, usually just the reactants. But we usually stick a proportionality constant in the front. What do we call that proportionality constant? Yeah, lowercase k, the rate constant. It's a lowercase k, by the way, because we're going to deal with k's all night long, right? That's the lowercase k, the rate constant. And we usually have some exponents here that we call the what? Those are the orders. So x here would be defined as the order with respect to reactant A. Y would be called the order with respect to reactant B. What would be the overall order of this rate law here? X plus Y. You just add them together. All the individual reactant orders add together to give you the overall reaction order. Cool. Where do you get these exponents, these orders from? They come from experimental data, typically. They come from experimental data. Here's the deal. So do they come from the coefficients? Sometimes. Sometimes they do, sometimes they don't. Turns out there's only one kind of reaction where you can get them from the coefficients. And it's a reaction that can't be broken down into anything simpler. What do we call those reactions? Elementary reactions. When you have an elementary reaction, one that can't be broken up any simpler, well, for those, it's going to be the coefficients that are the orders. However, did I tell you this reaction was elementary? No, then we have no idea if it is or not. So we don't know if these are both going to be 1 based on the coefficients here. We just don't know. So normally you got to figure it out from experimental data. So the ideology is this. Let's say the restroom is right across the hall, by the way, in case you're wondering. How long do you think it'll take me to get to the restroom from here? 10 seconds? Anybody else want to guess? 13 seconds? Sweet. The correct answer is you don't know, because you don't know what pathway I'm taking to get there. I neglected to mention that I was going to stop by Boston on the way, just so I could make fun of the Red Sox fans and be like, ha, you guys have lost 5 games in a row. And then I was going to hop back on a plane and get back here and then go to the bathroom. It's not going to take 10 seconds, just so you know. Because you didn't know what pathway I was going to take to get there, you couldn't tell me. Same thing here. The overall reactions A plus B goes to C. But what's the pathway that A and B combine in to get to C? A and B could turn into D. Then D could turn into E. And then E could finally turn into C. And it could be a multi-step pathway. Now, when we write a pathway out or a mechanism, we usually only include elementary steps for those. And so now you have 2 ways of knowing if something is an elementary reaction. If the problem says, for this elementary reaction, well, then you know it's elementary, obviously. The other way you'll know, though, is if you have a mechanism, which is a series of steps, often marked slow and fast, those are always composed of elementary reactions. But if it's just a general reaction given, it might be, it might not be, you just don't know. And so these orders have to be determined from experimental data. So, and this is one of the more important concepts of this chapter. Let's take a look at how we do this. So we have this lovely reaction. This is the overall reaction. You're not told whether it's elementary or not, so you have to assume that it's probably not. Could be, could not be, but we don't know. But the general rate law would look something like, in fact, let's put it up here. The general rate law is going to look something like, so reactant and your other reactant. And we don't know what those orders are. If I'd known this was an elementary reaction, I'd probably know what those orders are, right? So my first question for you is, we don't know if this is elementary, but my question for you is, should I expect that it could be elementary? Do I expect it to be elementary reaction? And the answer is actually no. But that might not be intuitively obvious right away. Here's the deal. If I told you, dude, you'd never believe what happened to me this morning. I saw two cars crash into each other. Isn't that crazy? Isn't that mind-boggling? Doesn't that blow your mind? Does that really blow your mind that two cars crashed? In fact, I think I heard a couple of girls talking about cars crashing before we started. Is it really out of this world crazy that two cars crashed? No, happens all the time. You've probably seen it happen this year. But what if I told you, you'll never believe what happened this morning? 6 cars all converged on the same point in space from 6 different directions and collided at exactly the same time. If that actually happened, you'd probably think it was like a stunt, right? It was rigged. They were trying to do it, because it doesn't happen. Same thing with molecules. 2 molecules collide all the time. And molecules got to collide for a chemical reaction. But for even 3 molecules to all collide at exactly the same moment in time, it's not a very likely event. So for this to be an elementary reaction, what it would mean is that 2 molecules of NO and 1 molecule of Cl2 would all have to collide at exactly the same time. That is not very likely. So what we see, if there's 1 reactant molecule in an elementary reaction, we call that unimolecular. If there's 2 molecules involved, we call it bimolecular. But if it's more than 2, if it's 3 molecules, we call that termolecular, and those are super rare. Unimolecular and bimolecular elementary reactions happen all the time, but termoleculars are super rare. In this case, if this were elementary, it would be termolecular, and so that's why right off the bat I'm saying, it's not so likely that he's an elementary reaction. I highly doubt it. Don't know for sure, because there's a couple out there, but probably not. So let's look at the experimental data here. So you are given a lovely chart, and in this chart you got the initial concentration of NO, the initial concentration of Cl2, and the initial rate. And it is just from such a set of experimental data that we are actually going to determine the rate law. So before we look at that, let's look at one other thing real quick. So say I ended up having a rate law that looked like this. We call this 0 order. What's anything to the 0 power? 1. What's the rate of this reaction equal to? Just K, because this is 1. What if I tripled the concentration of A? Would that affect the rate? No, because 3 to the 0 power is still 1, and rate still equals K. That's what a 0 order reactant looks like. It does not affect the rate at all. In fact, we probably just wouldn't write that, because anything times 1 is itself. So a 0 order reactant doesn't affect the rate of a reaction at all. Let's say, on the other hand, that instead of 0 order, it had been 1st order. And notice, if it's 1st order, do I have to write the 1 there? No, I can just leave that out. If there's no order written, it's implied that it's 1. So if it's 1st order, so in this case, the rate's equal to K times A. What would happen if I tripled the concentration of A? What would happen to the rate? It would triple. Because instead of being K times A, the rate would be K times 3A, which is 3 times bigger. That's indicative of a 1st order reactant. You triple the concentration of A, it triples the rate. They're proportional in a 1st order, for a 1st order reactant. Okay, your third likely situation is where maybe it's 2nd order instead. So now let's say it's 2nd order with respect to A instead. And in this case, if I triple the concentration of A, what would happen to the rate of the reaction? Yeah, it would go up by a factor of 9, because tripled squared, 3 squared, is 9. If you triple that, it gets squared, so the rate goes up by a factor of 9. And those are your most common orders, 0, 1, and 2. Every once in a blue moon, you'll see a 3rd order, but it's highly unlikely. But let's just say this happened to have been one of those really highly unlikely 3rd orders now. What would happen to the rate if I tripled the concentration of A now? It would increase by a factor of 27, because 3 cubed is 27. Everybody cool with that? How that kind of... So the greater the order, the greater the impact that particular reactant has on the overall rate of the reaction. Okay, so we're going to keep that in mind here for a sec when we're looking at this lovely experimental data. So the way to properly interpret this, so let's say you got a problem, and your problem is you're a poor college student. I know most of you guys are going to really have to try and pretend that you're a poor college student. So And here's the deal. Your car breaks down, and you can't afford to take it to the mechanic. But you're good with a wrench, you're good with a ratchet, so what do? So, well, it turns out your car doesn't start, doesn't turn over, doesn't anything. And you figured it out that it's either the battery or it's the starter. It's one of the two. And so rather than taking it to a mechanic and letting them fix it, you go down to AutoZone and you buy a brand new starter and you buy a brand new battery. And you replace them both. And your car works now. Was that the cheapest way to go, though? No, you replaced two parts. Only one of them was bad. So you replaced them both. The car works. So then which one was the problem? You don't know. Because you changed too many variables at the same time. Because you switched out both the starter and the battery at the same time, one of them was the problem, but you still don't know. But what if you go back in time for a minute and you switch out just the starter only? And now all of a sudden your car works. What do you know? The starter was the problem. And what do to save some money? You take the battery back to AutoZone and get your money back, at least for that. You just got by as cheap as you could. You did the work yourself, and you only had to replace one part. That's the ideology here. We have two reactant concentrations here. We have 3 trials we performed with differing amounts of these two reactants. And then the rate was actually measured. You guys kind of did this in your Crystal Violet lab a little bit. The idea is this. If you compare 2 trials, you want to pick 2 trials where only one of the 2 initial concentrations changed. And that way, if only one thing changes, then he's responsible for any change in the rate. So if I want to find out what's the order with respect to NO, then I need to pick 2 trials where only his concentration changed. His didn't change at all. Which 2 trials should I compare to find the order with respect to NO? So yeah, let's compare the second and the third. The concentration of Cl2 didn't change at all. Only the concentration of NO changed. What did we actually do to this concentration? It doubled. So during that same period of time, what did the rate do? Not 8 times. So yeah, it turns out 1.44 divided by 0.36 is 4. So it quadrupled. And if we look at kind of how that matches up here, we doubled the concentration of NO, but whatever we do to it is amplified by an exponent of x. And what did the rate do? It quadrupled. What happened to the k value, the constant between those 2 trials? It stayed the same. So essentially that means it's k over k. That's what we're really doing there. That's 1. That goes away. How did the Cl2 concentration change in those 2 trials? It was the same as well. And so it'd be 0.2 to the y over 0.2 to the y, and that cancels. So by picking 2 trials, we eliminated a bunch of variables. And what's x? Sweet. X is indeed 2. So we just found out its second order with respect to NO. What 2 trials should I compare to get the order with respect to Cl2?
How do you know not to use the first one and the last one?
Question is, how do you know not to use the first one and the last one? So if I use the first one and the last one, I'd be changing out my battery and my starter at the same time. You can't have both reactants changing at the same time. That way, when the rate changes, you don't know who's responsible for what. So you want to pick 2 trials where only one of them changed. And so that's why by picking the second and third, he's not changing at all. It's all him. And if the rate changed, we know he's responsible. Cool. So what 2 trials should I compare to find the order with respect to Cl2? Awesome. We'll look at the first and second. In this case, it's only Cl2's concentration that's changing. NO concentration remains constant. And since only Cl2's concentration changes, if the rate changed, Cl2 is responsible. Did the rate change? Yeah. So in this case, by what factor did we increase the concentration of Cl2? Good. Again, times 2. And by what factor did the rate change? Times 2. And so in this case, we kind of matched it up with our generic rate law. The concentration of Cl2 doubled, but again, that gets amplified to the y power. And what did the rate do? It also doubled. And again, because I picked the right 2 trials, the k value in both trials is the same. And so again, it's kind of like you have k over k, and that goes away. And the concentration of NO between those 2 trials was 0.1 in both cases. And so again, it's kind of like you have 0.1 to the x over 0.1 to the x, and that goes away. And so all you're left with is 2 to the y equals 2. So what's y? Good. What's the overall order then for this lovely reaction? 3. If we look at that rate law now, we now know that the rate equals K times NO to the second power times Cl2 to the first power. And so again, from the get-go, we said, is this likely to be an elementary reaction? And the answer was no. And now my question is based on finding out the rate law, is there a chance it's an elementary reaction? Well, there's a chance, because the orders do match up with the coefficients. That doesn't guarantee that it's going to be elementary. It might be. I'd have to do some more kinetics experiments to figure it out. It's still probably not, though, but it actually has a chance of being elementary. Still not likely, but it has a chance. So if I wanted you to figure out the value of K now, that's the next question on your handout, what would you have to know to be able to mathematically solve for the value of the rate constant K? You have to know the concentrations and the rate. Well, shoot, we're screwed, right? No. Do I have any times where I might know both concentrations and the rate? I have 3 such situations. Pick one and plug the numbers in. So because I rigged the data and I picked it, you'll get the same answer for K every time. On a test, though, if they give you real experimental data, they may come out a little bit different, but they'll be pretty close in that case as well. So in this case, if we rearrange this and solve for K, so here K, rearranging equals the rate over the concentration of NO squared times the concentration of Cl2. And I'm just going to plug the first trial's numbers in. And so here, K equals 0.18 over 0.1 squared times 0.1, just 0.1. And if we go through and solve, you'll get K equals 180. Now, it turns out this rate constant has units. It has units. But most of the time, if you look at your multiple choice answers, only one of them is going to have 180 as an option. So they don't usually have 3 answers that are all 180 and the only difference is the units. Although I have seen that question once, and because I have seen it once, I'm going to go over how you get the units out of this as well. There's 2 ways to get the units. The easy way and the hard way. We're going to talk about the easy way first. So here's the deal. Your units, you always have a seconds to the minus 1 in your units, every time, no matter what. You always have that as part of your units. The question is you'll also have a molarity term in here as well. And the deal is this, the shortcut, it's a pure coincidence, but the shortcut is this. What was our overall order for our rate law again? 3rd order. It turns out your molarity term and your seconds term, those exponents, if you add them together and take the absolute value, it should be the same as your overall order. So in this case, -2 and -1 is -3, and the absolute value of that is 3. And it's a 3rd order reaction. So that's the cheat. It always works out that way. So if it was a 2nd order reaction instead, this would have only been m to the minus 1, s to the minus 1. So had it been a 1st order, then it would have simply just been s to the minus 1, and then it would have been no molarity term. So here's the deal. The other way to get this is just include units. On the chart on your handout, there's units. What was the units for rate on the table? Molarity per second. And the concentrations were all given in terms of molarity. And the units will fall right out. Notice one of these molarities is going to cancel. So in this case, maybe I say this molarity and this molarity cancels. And so I'm left with this molarity squared, but it's on the denominator. And so being in the denominator, it'd be m to the minus 2 would be one way to say it, which is the same as 1 over molarity squared. And this is also seconds in the denominator. It was molarity per second. Another way to say that is seconds to the minus 1. And so if you just plug the numbers in with the units, these units would fall out of that anyways. Any questions on the rate constant K and potentially its units? Awesome.